Hey students, the first topic, that is Daniell cell. You know, in your Daniell cell, we use two electrodes. One is your zinc and one is your copper. Zinc behaves like the anode in the Daniell cell. Copper behaves like the cathode. The moment of electrons in the Daniell cell is from anode to cathode. The direction of current in the Daniell cell is from cathode to anode. In the Daniell cell, there are two moles of electrons which are exchanged between anode to cathode, right? And this is how you exactly represent your Daniell cell. In the middle, you have got a salt bridge. On the left side, you are writing the anodic part. On the right side, you are writing the cathodic part. Perfect. What happens when the Daniell cell works? The thickness of the zinc rod decreases, thickness of copper rod increases. Now, what is a salt bridge which we use in the Daniell cell? Salt bridge, it's basically, you know it is the inverted U-type tube which contains inert electrolyte mixed with gelatin. And what do we get at the end? We get a jelly-like paste which is fitted in that inverted U-type tube. Now, what are the functions of the salt bridge? You already know salt bridge. It completes the internal circuit. It maintains the electrical neutrality. It avoids the liquid-liquid junction potential as well. Now, my dear students, the inert electrolyte which we use in the salt bridge, what kind of behavior it should show? My dear students, whatever inert electrolyte you are using in the salt bridge, remember one thing, the cation and the anion of the inert electrolyte, they should have same ionic mobility. That means their speeds should be the same. The cation and anionic speeds of the inert electrolyte, they must be same. Then only the liquid junction potential will be avoided. Okay. My dear students, how do we represent the cell? Well, you know, in the middle, it's a salt bridge. On the left side of the salt bridge, we always write the anode. On the right side, we write the cathode, right? Okay, and this is how you exactly represent your Daniell cell, right? See, your zinc gets converted into zinc dipositive in the anodic part. In the middle is the salt bridge. On the right side, you have got cathode, right, at which reduction takes place. Copper dipositive gets converted into copper solid. Perfect. Before going ahead, I would be sharing the PDF of this particular session as well, and it will be shared in the Telegram t.me/WASSIMSIRCHEM. Right? This is the Telegram channel on which I shall be sharing the PDF of this particular chapter. Okay? Perfect. Moving on to electrode potential. How do we define the electrode potential? It is the potential difference that exists between the rod and the electrolytic solution. Right? And when this electrode potential is measured under standard conditions, which involves pressure 1 bar, concentration 1 molar, temperature constant, generally 25 degrees centigrade, at that point of time, whenever you measure the electrode potential, that's what you call as standard electrode potential, which is represented by E naught. Now, this standard electrode potential is of basically two types. One is called as standard oxidation potential, SOP. Another one is what you call as standard reduction potential, that is SRP. Now, for an element, SOP is always equal to minus times its SRP. Now, my dear students, what is the significance of the standard electrode potential? Do remember, more the standard oxidation potential of a species, more is its tendency to undergo oxidation, better the reducing agent, more the reducing power. Similarly, more the SRP of the species, more is its tendency to undergo reduction, better the oxidizing agent, more will be its oxidizing power, right? And similarly, you would have heard about the standard hydrogen electrode that is taken as the reference electrode whose SOP as well as SRP, both the values are taken as 0, right, as per reference. Now, talking about the EMF, how do you exactly define the term EMF? EMF is nothing, it is just the maximum potential difference between the two electrodes when the cell is not in use, right? And how do we calculate the standard EMF? E naught cell, it is E naught of cathode minus E naught of anode. E naught of cathode means SRP of cathode, E naught of anode means SRP of anode, right? Similarly, moving ahead, there are few results which you need to remember, and from these results, questions are directly asked. First result is between delta G and E cell. My dear students, delta G for the cell is equal to minus NF E cell, where N represents number of moles of electrons exchanged, F represents the Faraday's constant, and E cell is basically your EMF of the cell. Now, when you calculate the standard Gibbs free energy change for the cell, it is minus NF E naught cell. Perfect. Now, the most important part of this chapter, that is Nernst equation, right? How do we write the Nernst equation first of all? In this format, E cell is equal to, E cell is the EMF of the cell under non-standard conditions. E naught cell is the standard EMF minus 2.303 RT divided by NF log of QC, where QC is the reaction quotient, right? And my dear students, the modified form of Nernst equation which we use in the questions, that is E cell is equal to E naught cell minus 0.0591 divided by N log of QC, right? Now, you can make millions of galvanic cells, right? You just have to take two electrodes, connect them externally and internally, you will be getting a galvanic cell. Now, what is the condition for that galvanic cell to be working? My dear students, for the galvanic cell to be working, for its cell reactions to be spontaneous, delta G for the reactions should be negative, or you can say EMF of the cell should come out to be positive. And my dear students, when the galvanic cell works, a stage arises, that's what you call as equilibrium stage. At equilibrium, the potential difference between the electrodes, that becomes zero, and cell at that point of time does not work. So at equilibrium, your E cell as well as delta G for the cell, that comes out to be zero. Okay. Now, the point is, how do we calculate the oxidation potential and reduction potential of the half cells under non-standard conditions? Or I can say, how do we calculate the oxidation and reduction potential of the electrodes under non-standard conditions? For that purpose, again, we'll be using the Nernst equation only. Have a look. Oxidation potential of the half cell is equal to standard oxidation potential of the half cell minus 0.0591 divided by N and log of QC. Similarly, how do we calculate the reduction potential of the half cell? ERED is equal to E naught RED minus the same result, right? And how do we calculate the EMF of a complete galvanic cell, of a complete cell under non-standard conditions? This is the result. E cell is equal to E naught cell minus 0.0591 divided by N log of QC. Now you must be thinking how this QC expression is to be calculated. For example, this is your balanced chemical equation. How do we write its QC expression? Before writing the QC expression, you should know whenever you see any reactant or product in the aqueous phase, right, its active mass is taken as its concentration. If you see any reactant or product in gaseous state, its active mass over here will be taken as its partial pressure. If you see any reactant or product in pure solid or pure liquid phase, their active mass is taken as unity, right? Now, QC is equal. Start with the product. This is the product which is in solid form, nothing to do with this. Now, moving on to this product, right, which is in aqueous state. So, concentration of D raised power N4 divided by concentration of A raised power N1. This is in gaseous phase, partial pressure of B raised power its stoichiometric coefficient, that's N2. Now, one more thing that's important. What is that? Concentration cells. In concentration cells, what do? We use two same electrodes, right? If we are using two same electrodes, that means E naught cell has to be 0. So whenever you see any complete cell involving two same electrodes, first thing that should come into your mind, that is its E naught cell will be 0, right? Same electrodes are used. Now, this concentration cell is basically of two types. One is called as electrolytic concentration cell. One is called as electrode concentration cell. In electrolytic concentration cell, what do we have? In electrolytic concentration cell, we keep the concentration of electrolytes in both the containers, anodic container and cathodic container, as different, due to which EMF gets generated. Similarly, in electrode concentration cell, what do? We keep the partial pressure of the electrodes different, by means of which EMF gets generated. And once EMF gets generated, cell automatically starts working. Now, these are again two important points which you need to remember. Reduction potential of the half cell, reduction potential of the electrode is directly proportional to the concentration of electrolyte kept. If you keep the concentration of electrolyte more in the container, the reduction potential of the overall electrode will be more. And if less, then reduction potential will be less. And inverse is the relation with the oxidation potential, right? If I move ahead and talk about a few more things, that is thermodynamics of the cell. How do we calculate delta G for the cell? Minus NF E cell. Do you know it, right? How do we calculate delta S? Entropy change for the cell reaction is equal to NF dE upon dt, where dE upon dt is called as temperature coefficient of the cell, right? And if you got delta G for the cell, if you got delta S for the cell, you can calculate delta H as well. This is the relation, right? You know delta G is equal to delta H minus T delta S. From that particular relation, you can calculate delta H for the cell as well. Now guys, talking about products of electrolysis, right? When you do the electrolysis of different electrolytes, right? What are the products of electrolysis which you get at anode and cathode? Three main I have mentioned over here. You're supposed to remember them. When we do the electrolysis of molten NaCl, at cathode sodium gets deposited, at anode chlorine gas gets liberated. NaCl aqueous, at cathode hydrogen gas gets liberated, at anode Cl2 gas gets liberated. aqueous CuSO4, right? When you do its electrolysis, at cathode copper gets deposited, at anode O2 gets liberated, right? And over here, during the electrolysis of all these three electrolytes, do remember the electrodes are basically your inert ones, okay? Now, moving on to Faraday's first law of electrolysis. What Faraday's first law of electrolysis is all about? My dear students, is a very simple thing. Since during electrolysis, either metal gets deposited or gas gets liberated, right? Now, the amount of substance deposited or liberated at any electrode, that is directly proportional to the charge which goes into the solution. More the charge going into the solution, more will be the amount of substance either deposited or liberated at the electrode. And this is the result by means of which you can calculate mass of substance deposited or mass of gas liberated at a particular electrode. Similarly, this is the result by means of which you can calculate the moles of substance deposited or liberated at a particular electrode, where E stands for the equivalent mass of the substance, I stands for the current which goes into the solution, T is the time duration in which the current goes into the solution. Similarly, what is your Faraday's second law? Say, my dear students, Faraday's second law says that whenever you have got two or more than two electrochemical cells, or I'll say it like this, whenever you have got two or more than two electrolytic cells containing different electrolytes connected in series, do remember the gram equivalence deposited or liberated at every electrode will be the same, right? Whatever electrode you have, gram equivalence deposited or liberated at every electrode is definitely going to be same. Now, my dear students, over here you would have seen this n factor, right? How do you calculate n factor of different substances? Whenever you see a balanced chemical equation like this, right? For example, you have to calculate n factor of A. It will be electrons exchanged 12 divided by its stoichiometric coefficient, so 12 by 2. This is going to be 12 divided by 3. This is going to be 12 divided by 6. This is how you exactly calculate n factor of different substances in a complete balanced chemical equation. Number of electrons exchanged divided by its stoichiometric coefficient. Now, talking about few more terms about the conductance part. The first thing is the resistance. Resistance of the conductivity cell. Resistance of the electrolytic conductor, right? It is something which you all must be knowing. It is the obstruction in the flow of the current. How do you calculate this resistance? It is nothing but R is equal to rho L by A, where L is the distance between the electrodes and A is what? And A is the area of cross section of that part of the electrode which will be inside the electrolytic solution. Then you have got resistivity, this particular formula. You have got conductance, which is defined as inverse of resistance, right? Its unit is Simon, particularly. Conductivity, 1 by R into L by A. This L by A particularly is called a cell constant, right? And the units of kappa over here is Simon centimeter inverse. Molar conductance. How do you define the molar conductance? It is defined as the conductance shown by 1 mole, conductance shown by the solution, conductance shown by the electrolytic solution when 1 mole of electrolyte is present in a given volume of solution. Perfect. This is how you calculate molar conductance. Molar conductivity, kappa multiplied by 1000 divided by normality, right? When it's to be calculated in Simon centimeter square per equivalent. Now you should remember with dilution, molar conductance, equivalent conductance, they increase, but conductivity, it decreases, right? Conductivity decreases, and it's valid for both weak as well as strong electrolytes. And the last topic, which you all must be knowing, that's Kohlrausch law. Kohlrausch law says that the equivalent conductivity at infinite dilution of an electrolyte is basically the sum of their ionic conductivities, and this is how you write the statement. And its main application is to calculate the degree of dissociation of a weak electrolyte. How do you do that? Molar conductance of the weak electrolyte at a given concentration divided by molar conductance of the same electrolyte at infinite dilution. Similarly, molar conductivity of a sparingly soluble salt is nothing but kappa multiplied with 1000 divided by solubility or molarity when you have to calculate it in Simon centimeter square per mole. My dear students, this was a very quick revision of the chapter Electrochemistry. I believe it will be properly clear to you now. I have already taken its marathon, right? From the marathon, it would have got cleared in detail, and from this particular session, I believe all the important things which I have to share with you, I have conveyed them all over here. So with this, I'll be taking a leave. I'll keep on coming up with all these such sessions, and for those sessions, please do subscribe to this particular channel and do hit the like button on this particular session as well. So with this, I'll be taking a leave. Take care. God bless you all and love you all, guys. Bye-bye.